seconds.
Alright, you're recording.
Alright, hello there. We today are going to talk to you about the Bernoulli's equation. The Bernoulli's equation is one of the most fundamental equations relating to fluid mechanics, hydraulics, as well as aerospace applications. It was proposed by physicist Daniel Bernoulli in 1738. The Bernoulli's equation relates velocity, pressure, and elevations of steady flow for an ideal fluid. It also relates geometric conditions to flowing conditions at any given point where the area and velocity are known. Bernoulli came about this equation after he discovered that as velocity of a flowing fluid increases in a pipe, the pressure of that fluid decreases. The Bernoulli's equation is very helpful in figuring out the forces present in a flowing fluid. The Bernoulli's equation can best be described as the conservation of energy for flowing fluids. The conservation of energy method can allow for friction by assuming a loss of energy expressed in terms of potential energy between the two states. This loss of energy is better known as the head loss in fluid mechanics studies. And for this conservation of energy equation, here's your normal one with the pressure and everything. It normally equals some constant. But for the conservation method, you have your initial pressure over the specific gravity of that fluid plus the height, the elevation of that some arbitrary datum, plus the velocity head, which is the velocity squared over 2 times the gravity equals the pressure in your second state over that same specific gravity, of the fluid, times your second elevation height, plus the second part of your velocity head, times that. Now, in cases where there's friction present in the pipe, there's also a head loss that can be assumed. And for the assumptions that go into the Bernoulli's equations, I'm going to hand it over to Alden Tate.
Alright, I'm talking about the assumptions. Since there are a number of variables in this equation, it's important to understand and recognize certain assumptions that must be made when using this equation. Some of these basic assumptions are: friction effects must be negligible, and it assumes flow is steady. The equation applies along a streamline. This assumes the fluid to be incompressible. This makes the specific weight constant. It assumes that no energy is added or removed to the fluid along the streamline. This means that external forces must be conserved, density is constant or a function of pressure, and the velocity must be derived. If we do not account for these assumptions, serious errors can result. Although the Bernoulli's equation is sometimes applied to real fluids with good results in situations where friction effects are negligible. And here's Zeke for an example.
For an example of Bernoulli's equation, we have a pipe in a processing plant flowing with glycerin. Glycerin has a specific gravity of 1.26. The initial diameter of the pipe is 600 millimeters and the pressure is 300 kPa. The pipe starts at our datum here and goes down 1 meter to where the diameter is 300 millimeters and the pressure is unknown. We know that the flow rate is 700 liters per second. So the first thing we need to do in order to find out the pressure that we have at the end of our pipe or at the exit is to find out the velocities at the beginning and at the end. We'll do this using the flow rate and the area at the beginning. So V1 at the beginning is equal to 0.7 cubic meters per second, which is the 700 liters per second in meters per second. And that's going to be divided by the area of our pipe, which is pi times 0.3, or the radius, meters squared. This equals 2.48 meters per second. Knowing that the flow at the beginning and the end of the pipe have to be the same, we can go ahead and find out velocity in the second part of the pipe. So if our flow rate is 700, we know that this area is 4 times greater at the beginning than at the end. So we can actually make this simple and be our V2 equals 4 times our V1. And that comes out to equal approximately 9.90 meters per second. Now, coming back over, we can use our Bernoulli's equation, and we'll fill in the parts that we already know. We have the first pressure, which is 300 kPa, times 1.26 specific gravity, times the weight of the water, which is 9.81. Since the datum is at the beginning of our pipe, the height will be 0. And then we'll add in the velocity head. The velocity head is 2.48 squared divided by 2 times the acceleration of gravity. And this is equal to our second point. The second point has the unknown pressure over the same fluid. Plus or minus the 1 meter down. And then we're going to have the velocity at the end, which is 9.90 squared over 2 times the acceleration of gravity. When we calculate all this out to find the pressure at 2, the pressure comes out to be P2 equals 254 kilonewtons per meter squared, which is the equivalent of 254 kPa. So there we have the excellent use of Bernoulli equation to find unknown pressure in an example.